Let's talk about the gas law simulation lab. So I want to walk you through what you need to do for this and what we're trying to accomplish. The idea for this lab is to understand the four variables that affect gases. And actually, this is the lab itself. But if you click on this link, it will take you to this website with this simulation. So let's take a look at it. So the four variables that we have to deal with gas laws are temperature, volume, pressure, and moles of gas. So looking at this, it's pretty obvious to see that we have our temperature here, and we can influence that by heating or cooling the gas. Volume is here, it's measured in liters, and we can raise or lower that. So actually, let me show you. So we can heat this gas up a bit, and it's going to have an impact on everything you see here, all these other variables, and we can cool it down a bit, same thing. We can increase the volume, and we can also decrease the volume. And we can also hold everything really constant if we wanted. So you can lock that and unlock it. Temperature, you can choose whether or not you want to affect it or not. Our pressure gauge here is not something that you can directly affect, which is usually the case, but it's something that changes in response to other variables, but it is a variable to play around to know about. Moles of gas you can control by adding or removing gas. So for example, this little lever here will allow you to remove gas. If you press the pump, you can add gas. If you can turn off and on which gases you use. So you could add, there's two different gases you can play with here. There's gas B, which is a little bit bigger. And there's gas A. You can add both at the same time or just one at a time. So that adds some of both. Let's just empty the tank out again, just to start from the beginning. Let's just add gas A. And as you do this, you're going to notice these numbers will change as well. So there's a lot of things to pay attention to. Every time you make a change, you should definitely look at the gas particles themselves. This is a great model of what, like why everything changes. And I think just thinking of these as little bouncing balls bouncing around is pretty effective. It pretty much explains the whole scenario here. The pressure is related to how often they're hitting the sides of the tank, which we'll learn more about later. The average kinetic energy is how much speed, not really speed, but like movement, energy of movement they have. And the RMS, I don't remember what that stands for, but it's like the actual speed. It's in meters per second. So how fast are the particles moving? So these two numbers here, as well as the pressure, are all going to change depending on what you do in this scenario. So your goal for this lab is to start figuring out what's going on here. What happens, just play around. What happens when you change the temperature or the volume or the moles of gas? And how does that interact with pressure? And how do these four variables all relate to each other? So let's look at the lab itself, and we'll see what questions you need to answer, and that might help. Oh dear. Just waiting for the bell to go off. All right, so there are a total of 5 questions in this lab. So let me show you what each of them, and they're kind of divided into 3 sections. The first 3 questions are very specific. I'll give you very specific instructions of what to do and what you're looking for. So that's questions 1, 2, and 3. Question 4 is asking about proportional versus inversely proportional relationships. So identifying each of these as proportional or inversely proportional. And then 5, there's multiple steps that talk about A versus gas B. So the first page is the most important, and that's what we'll focus on at the moment. So let's take a look at number 1. Number 1 says, what happens to the molecules of gas if you lock the volume and number of moles? So we do not change those, we keep those constant, but we change the temperature. So what do we see happening to the molecules of gas, and how does it affect the pressure? So let's take a look at our simulation, and we'll answer this question. Okay, so the first thing we're going to do is we're going to lock the volume so that it does not move. And we're not going to add any gas A or B. We're just going to leave that alone. So the only thing we're going to change is the temperature. So before we do anything, I'm taking a look at these molecules. I'm seeing how they're bouncing around. It seems kind of random, but they're all moving. I note that the pressure is at 1 atmosphere. The average kinetic energy is about 3.8, and our RMS, or our speed of the molecules, is 1,592. So let's see what happens when we heat this up past 305. It's get pretty hot. Okay, that's really hot. So just taking a quick look, what has happened to these molecules in the gas chamber? Well, it looks to me like they're moving quite a lot faster just by looking. And our data over here would agree. The kinetic energy has more than doubled. We went from 3.8, well, maybe not quite, but 3.8 to like 6.8. So that's definitely higher. And the actual speed has also increased. We were at like 1,500. Now we're at like 2,100. That's very different. The pressure was at 1 atmosphere. Now it's at 1.79 atmospheres. So those are some great observations that we can make and great answers to that question. Let's see what happens when we lower the temperature, when we cool it off. So we'll cool it a little more. So if we cool it here, we can see that the molecules are moving more slowly. The kinetic energy has decreased, the speed of the molecules has decreased, and the pressure has also decreased quite a lot. So those are some notes. That's how we would answer number 1. So going back to number 1, we could write in something to that effect. The molecules have slowed down when you cool it, or they speed up with heat as you heat it up. And the pressure increases when the temperature increases. The pressure decreases when the temperature decreases. Okay, so that's what you could write there. I'm not going to write it for you. You can do that yourself. Okay. So number 2 and number 3 are going to be very similar. It's a little different. The first one, for number 2, you're going to keep the volume locked, and you're not going to change the temperature, but you're going to add or subtract molecules using that pump. For number 3, you're going to keep the temperature and number of molecules the same, but you are going to change the volume and see how that affects the molecules and the pressure. Okay. So that's your data that you need to collect. The next section is asking about whether or not these relationships are proportional or inversely proportional. So let me explain what those two things mean. I have some notes here for you. Okay, so directly proportional means that there's a direct relationship between variables. Proportionality, it's about how does changing one variable affect another variable. So a direct relationship means that they both change in the same way. So for example, if you have X and Y, if something is directly proportional, then when X increases, Y will also increase. Sorry, that's an upwards arrow in case you couldn't tell, it's a little messy. There we go. When X decreases, Y also decreases. So they change in the same way. So an example I like to use for this one is the weather outside versus how much ice cream people eat. So as the outside temperatures rise, people eat more and more ice cream. As the temperatures go down, people eat less and less ice cream because it's cold. So that's a directly proportional. These two variables are directly proportional to each other. Ice cream, amount of ice cream eaten, and weather are directly connected. They change in the same way. Now, it might not be a one-to-one thing. You know, for every degree outside it increases, it doesn't mean people eat one more ice cream, but there's some sort of connection between the two. Inversely proportional is kind of the opposite. This is when the two variables have an opposite relationship. So in this case, when X increases, Y would decrease, and when X decreases, Y would increase. So a great example of this is weather, the temperature outside, and how often people wear sweaters, or how many sweaters people wear. So if the outside temperature starts to rise, people wear fewer sweaters. But if the outside temperature decreases, people wear more sweaters. So as temperature increases, sweaters decrease. As temperature decreases, sweaters increase. So they are inversely proportional. They are opposite of each other. So what we need to do for all of the variables in all of the relationships between variables that I've given you, we have to decide, are those two direct or inversely proportional? So let's go back to our worksheet. to our lab sheet. So at this point, I think we have enough data to answer one. Pressure and temperature. What happened when we increased the temperature? How did the pressure change? Well, if you remember, it increased. What happened when we decreased the temperature? Well, the pressure also decreased. So they are changing in the same way. So we would say that these are directly proportional or proportional, not inversely proportional. And you're going to need to do the same thing for all the other ones. If you're not really sure, you can always just go back to the simulation. So for example, pressure and volume, let's just kind of give that one a try. So we can't really measure, we can't really change pressure, but we can change the volume. So I'm just going to heat this up just a little bit. Okay, so we have the volume, it's at 751. What happens when we decrease the volume? Well, it looks like the pressure is increasing. So we're decreasing the volume and the pressure is increasing. What happens if we increase the volume? It seems like the pressure is decreasing. So increasing the pressure, the volume means decreasing the pressure. So that is an example of inversely proportional. The two relate to each other oppositely. When you increase one, the other decreases. When you decrease the volume, the pressure increases. So they respond oppositely to each other. So that is an inversely proportional relationship, whereas the other two were proportional. Okay. So that is that section. I think you all can handle the rest of this pretty well by yourselves. Sorry, I don't know if it's working right now. Share screen, sometimes it's a little strange. Okay, let's look at number 5 now. We've got to get the lights back on. So you're going to need to try playing around with gas A and B. The two of them are different from each other. Let's see what they are. Hold on. Lights, come on. There we go. Sometimes the lights come on, sometimes they don't come on very easily. Okay, so we're going to ask questions about A and B. So what are the differences between the gases? So think about size and speed, effect on pressure, temperature, and volume, all of that. What do the gases have in common? Again, think about size and speed and effect on pressure, temperature, and volume. And for equal numbers or moles of gas A and B, which do you think would have more mass? So if we actually put these on a scale, which one would weigh more? If you have the exact same number of them. And does the mass of a gas molecules affect the pressure, temperature, or volume of the gas? So does that make any difference? And why do you think we would use number instead of mass when we do gas-related calculations? So let me show you maybe a way to help play with this. So right now we are only looking at gas A. So there's just gas A. It's kind of moving around. When you hit the pump, it's going to add the same number each time. So let's just cool this off real quick and we'll actually be able to count these molecules a little more easily. Heat it up just a tiny bit. Okay, so 1, 2, oh gosh, how are we going to count these? 1, 2, 3. Yeah, I think there's like 10 of them maybe. Looks like probably about that much. So we have our current situation here. We can kind of see the temperature was 165. Let's empty this out. So there's nothing left. And let's just add gas B and we'll see what we notice any differences between the two. Okay. So there's gas B. Gas B obviously looks bigger. It looks like there's about the same number of molecules. You can kind of count on that. So you might want to start thinking, start heating it and cooling it and seeing how it affects the situation. You can also look at these numbers to see if their kinetic energy is the same or their speed. So yeah, let's just try A again. It's just kind of a matter of playing with these numbers. I actually noticed that all 3 of these seem exactly the same. If I just kind of empty it and put B in, yeah, that was 406 in 1 atmosphere and 165. So that's kind of interesting. But yeah, just kind of play around with gas A and gas B. You can empty out gas A, put gas B in, you can mix them together and see if you can answer those questions based on that. Can be a lot of kind of fun. So again, hopefully by the end of this, this idea of the relationship between these four variables, and you'll have a pretty good, I hope that you have a good understanding of what volume means. What does pressure mean? What does temperature and moles, like what do those things mean on a more intuitive level? And honestly, like this simulation is so good because that's what I see in my head when I think about gases. I've kind of internalized that. So that's the main focus for this, is to really understand what is a gas and how does it change. Why does it, how can we explain its behavior based on these different variables? So give that one a try and let me know if you have questions as always. Thank you all.